The app was called CamFind, and the idea was, okay, if you're interested in something in the physical world, wouldn't it be cool to just take a picture of it, anything you're interested in, instantly you would know more about that, and you could find it on the internet. You'd see, search results for anything you're interested just by taking a picture of it, like a Google for the physical world. Well, that's an interesting idea, but how would it work? I mean, computer vision's great, right? But it can't exactly figure out everything. So in this idea of computer vision is sort of a smaller subset of the bigger world of artificial intelligence. And of course, artificial intelligence these days is a lot more artificial and a lot less intelligent. We still have a very long way to go to get to the point where we're truly dealing with something that's artificially intelligent. Now, I grew up in the 80s, and the thing about the 80s is we had a lot of different ideas about what artificial intelligence would look like. But I was really interested in this movie about a robot. And as it goes in this movie, this robot learns how to see, he learns how to feel, he learns how to touch and hear and understand the things that are going on around him. He even develops a personality. And so I really loved to build things when I was a kid. This is my 10-year-old mind's version of a pinball machine. But what was really cool is I found this article in a magazine that I used to read about how to build a robot out of one of these old microcomputers and a trash can. I can't actually, I figured, I found an image of these guys building one on the internet, which is pretty cool. But the problem with these things is that they would literally just drive around and bump into things. I mean, they were really good at following a set of instructions, but all they would do is just drive around and bump into things, which of course 20 years later became a feature. But that's just the thing, right? Like computers are very, very good at doing exactly what we tell them to. I mean, the idea of a software bug comes from the fact that a computer doesn't know what we mean for it to do. It just does exactly what we tell it to do, even if it's completely messed up. So when we first started experiencing this idea of speech recognition, it was really disappointing. I mean, we would say things like, do you recognize speech? And the computer would think we said, did you recognize beach? It had no clue. I mean, I still get on the phone with these IVRs and it says, say help if you want help. And I start screaming, help, 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 and people are looking at me on the street. I mean, if you think about the difference between the words there, and there, they all sound the same, but they have a completely different meaning depending on the context. And so it wasn't until Siri arrived that we really saw the first difference between speech recognition and cognition, or understanding the context and the bigger picture of what we were trying to say. Siri actually understood some of the things that previous generations of speech recognition did not. And this is the first example where we saw that it was more about cognition and understanding than just recognizing bits and pieces of speech. And so when we talk about artificial intelligence, I think it's really important to talk about understanding. And with understanding, we need to understand also that with humans, about 80% of the information that we process is visual, and only 20% is through documents or reading, and 10% is through sound. And so over 90% of the information sent to the brain is actually visual. We live in a visual world. Most of our human experience is visual. So I think we need to ask ourselves the question, well, why can't computers see? I mean, right now in the space of image recognition, and for a very long time, scientists have created these mathematical models of feature engineering that's been able to take a look at images like this, and it'll say things like, oh, okay, that's a Nike. But that's not a Nike, that's a Nike men's running shoe, right? So the problem is, until this point, now recently, scientists have made a huge jump forward in the state of the art with deep learning neural networks. And this is fantastic because essentially for the first time, it's become possible to do this with recent advances in hardware. GPUs, you might have been hearing this float around. What computers are basically doing now is creating mathematical models of the human brain in a computer. The way the brain works is essentially billions and trillions of connections of these neurons between synapses, and we can model that mathematically. What's also really amazing, and in fact, it's really cool, this question just came up in the last session. Scientists have been able to take this concept of neuroplasticity, or essentially the human brain, the connective tissue in the brain, though it's incredibly complex, is also beautifully simple. So the same tissue that knows how to see, or in this case, a tongue, can learn how to do something else. This person here is learning how to see through their tongue. Scientists have planted a bunch of little electrodes onto a popsicle and wired it up to a camera, and a computer translates the visual content coming out of the camera into the little electrodes on the tongue, and this person has learned how to see through their tongue. So what that basically tells us is, though the brain is incredibly complex, it's also beautifully simple. And the same type of structures that learn how to see, how to hear, how to talk, everything else, can be trained in multiple things. That's called neuroplasticity. So when we model a neuron in a computer, it's really pretty simple and pretty neat, just like the human brain. We have this mathematical model, and we let the computer figure out all the A's, B's, and C's to figure out what the inputs of the X and Y's are to solve the equation, just like we all did in math class. And what essentially starts to happen is, just through a series of trial and error, millions of trial and error, just like we do as humans, we learn about our environment as we grow up. We're constantly corrected. We try something, we make a mistake, we have a correction. The computer works the same way. We have an output that we want to achieve based on an input, and we slowly bring the output to match what we want it to be. So we feed the computer an image of a cat, and it says dog, and we say, no, that's a cat. And we feed it another image of a cat, and it says dog, and then we say, no, that's a cat, and eventually it learns that it's a cat. So there's a lot of really fascinating open source technology that's out there today that allows you to do, any programmer to do this just off the shelf. And what's really amazing is that now computers can classify images even better than humans can, and much faster too, often within milliseconds. But there's still a problem in that, look, if I show you this picture of a bike, it's not just a bike. You know what the handlebars feel like. You know the cold metal on your fingers. You know what it feels like to ride fast and have the wind in your hair. Computers can't do that. They don't. They just see this as, oh, that's a bike, or maybe it's a Cannondale bike. And the other problem is, so computers have a hard time recognizing the differences between things. This is a result of what a computer thinks a number 3 is and a number 4 and everything else. It has nothing to do with that, but it still thinks that. Well, take this picture, for example. You notice what you just did? Well, computer thinks this is Rust-Oleum, stops rust. Or maybe that it's a 68% can, 54% metal, 33% rust. I just think it's funny. This is another one. This is my favorite. This says wind seeker. This ride is currently closed to high winds. Well, okay, wind seeker. Maybe we read the text. We know it's a sign, carnival. Maybe we see, oh, it's a person standing in front of a sign at an amusement park. Oh, this one's good. Invisible spray. Right? Like, we get this in an instant. A computer has no idea what is that? You know, like empty shelf. So I think when we talk about computer vision and artificial intelligence, what we really need to talk about is meaning, is cognition and understanding. So what do? Well, just like we took the worlds of voice recognition and move them into voice understanding, I think we need to look and talk about visual cognition, visual understanding. After all, computers can now dream, which I still think is the creepiest thing in the world. But what if computers could see? Would they be able to read our emotions? Would they mimic our emotions to connect with us? Would we be able to say to Siri, hey, Siri, I've got this rash on my arm, and she says, okay, let me see that. Well, a couple of years ago, we started experimenting with this idea, and we wanted to help the blind and visually impaired. So we came up with this app for the blind and visually impaired where you could take a picture of anything, and it would speak back to the user what was in front of them. It was a scene or a specific object. And a couple of months ago, we got an email from one of our users, and it was really amazing, and so I'd like to share this message with you. He said, hello, my name is Danny. I am totally blind. I've been blind for 2 years now. And I've had a hard time adjusting, but ever since I found TapTapSee, I feel so much better about being blind. Now I know I won't miss out. I can see the pictures that my friends send to me and my family shares with me. Thank you so much for bringing back some joy into my life. People like Danny remind us how important it is to support the community and to support people through this idea of artificial intelligence and visual cognition. I think there's something we all can do to make life better for other people through artificial intelligence. Let's make it see. So I think we have some time now for some questions, Q&A session.
If you ask a question, I might hit you with this box. We cannot artificially intelligent your question. Let's see how I do. Ooh. It's padded. Maybe not
Is it
anymore.
on?
There we
yes.
go.
Hi, my name is Carsten. So you gave us a nice sort of background on deep learning and image recognition, pattern recognition, but how do you actually want to bring common sense into the AI world and give it all the knowledge, the system, give it all the knowledge that it needs in order to understand and not just recognize that there is something that resembles something else?
Yeah, exactly. So just as we learn about the world growing up, what essentially we're doing with computers right now is we're training them through, it's like if you were to turn off all your senses and just blink your eye for 30 milliseconds at a time to see images. It's not a very good way to learn about the world around you. So we've experimented with this idea of training computers through massive, massive quantities of images. We have over 600 images in our training set that we've used to train computers to learn about the world around it. And so what ends up happening is you start getting into the larger and larger data sets is that the computer starts doing this thing called transfer learning, where it'll learn about, say, a Starbucks coffee mug, and then it'll see a broken something, and then if you break a Starbucks coffee mug, then it says, oh, that's a broken Starbucks coffee mug, even though it's never seen one before. So that's kind of the first step. The next step is to turn on all the other senses, to have the sense of sound interconnected with the sense of sight, with emotion, with memory, with all these things that we as humans just take for granted. And that's what really provides a sort of cognitive understanding about the world around us, is that we don't learn by just little 30 millisecond blinks of our eye. We learn through a lot of different senses. And so I think it's important for us to get to the point where computers have a lot of that. With mobile devices, it's great because we have a lot of sensors on the device that we can have learning input from. But I think we still have a long way to go to get to the point where we can develop technology that's truly cognitive, that can reason and can understand about the world around it, because it takes a tremendous amount of training data. What we've done in particular is we've focused initially on this idea of creating a very, very, very massive data set that was specifically designed for training through visual cognition. But there's a lot more to do, and that's what we're really excited about as a company, is that there's a really, really long runway ahead to really develop this sort of cognitive understanding.
Cool.
Thank you. Anybody else?
We got a question in here? No, you're just like, it's a box. I think they're afraid because you talk really fast.
I was told this was a lightning round, and I think I have like 2 minutes left, so I was like, go, go, go. We have infinite amounts of energy up here, so it's... I'm like the Energizer Bunny.
Since I still have this thing, let me try with a follow-up. You said we. You mean we as a research community, or what is your contribution as a company going to be? How do you finance
Sure.
all of this?
Yeah, so as a company, we focused on this idea of being a platform as a service. And so as we've grown now, we've started getting deeper into like on-device and stuff like that. But ideally, we're a platform, so companies will give us their images and we'll provide the meaning or the understanding behind those images. So, we work a lot with the retail industry. We work a little bit with the marketplace apps. There's a lot of different apps that use us, especially because, they're on device and people take pictures and stuff to see what's around them. But yeah, as a company, we like to try to push the state of the art. We also are developing this gigantic database of training set. Which now, so if you look at the ImageNet training set, which is about 14 million images, ours is like profoundly larger at about 600 million images. So it really makes a big difference in terms of the way that we're able to dive deep into this idea of transfer learning and a bunch of other stuff that provides this level of cognition.
But surely the largest training set is what Google has. How can any company hope to compete with that?
Yeah, you would think so. But the challenge that Google has, and we've seen this too, I actually had a long background in web property development, is that the data itself is not specifically curated for training. Training data is really, you have to have very clean, very accurate, very consistent training data. The challenge that Google has is that they've scraped a bunch of images off the internet, or even the images that they have through different data sets are not specifically designed for this. They're much, much smaller scale. And so, if you think about it, we live in a very infinite world. There's a lot of different objects to recognize. There's a lot of companies right now working on this idea of image classification, which is absolutely fantastic. The challenge with that is that it's a very finite list of things that you can recognize. And so when we look at something like that, we say, okay, well, we would love for computers to be able to actually figure out what it's looking at. I mean, if I didn't know exactly what kind of chair this is, our idea is that the platform, which is something that we do, the platform should figure out at least enough descriptive detail about that chair in domain-specific language, so that the type of language that a designer might use to tell you about that chair. And then you might be able to find that chair on the internet. And then we can use that training data to continue to refine our data set as well. So then we'll know exactly what kind of chair that is the next time somebody takes a picture of it.
I think there's a question behind you, guy in the gray shirt.
My question is that why do you say that it's only about vision? I mean, the problem of context or cognition is also with other things like text, for example. Mm-hmm. I mean, it's not so easy for computers to understand the semantics of text.
Yeah, so when we talk about vision, we really kind of go back to the fact that most of the human perception and visual processing in the brain is vision. About 90% of our perception is visual. And so when we get excited about this idea of true cognition and understanding inside of computers, I think we really need to focus on vision as sort of like the keystone of that, and then move deeper in some of these other things. But yeah, you're right. I mean, the concept of cognition goes much beyond vision. And especially as we've seen in a lot of our users that are blind and visually impaired, okay, so they don't have vision, right? But they also see through the world through other types of perception. So what we think of vision isn't just limited nearly to the imagery, the visual media, but actually a lot of perception about our physical world, many of which we're just beginning to understand.
Amazing. Thank you so much, Brad.
Thanks again.